flow reaction turbines. Today in this class we are discussing about some problems regarding the axial flow reaction turbine. So let us look into the first problem. A Kaplan turbine develops 22,000 kilowatt at an average head of 35 meter. So the turbine is developing a power of 22,000 kilowatt and an average head is 35 meter. Assuming a speed ratio of 2, speed ratio is denoted by Ku, it is taken as 2, and flow ratio is given as 0.6. Flow ratio is given as 0.6. Diameter of the boss is equal to 0.35 times a diameter of the runner. So we know that diameter of boss equals 0.35 times diameter of runner. Diameter of runner is denoted by DO. And then overall efficiency is given as 88%. So efficiency overall is given as 88%. So we need to calculate the diameter, speed and specific speed of the turbine. So we are here in this problem we are finding the diameter, speed and specific speed of the turbine. So first of all we need to find the peripheral velocity, that is u1. So u1 can be obtained from the equation. So we know that u1 is equal to Ku into root 2gh. Ku into root 2gh. So from this equation we will obtain the value for u1. So u1 is equal to Ku is 2 into Ku is the speed ratio and it is given as 2 and into root 2gh. Root 2gh h is given as 35 meter. So u1 is obtained as 52.4 meter per second. That is the peripheral velocity of the runner. Okay. Next we need to find the flow velocity. So flow velocity, here it is given that flow ratio is given. Flow ratio is given as 0.6. So we know that flow ratio is equal to Vf1 divided by root 2gh. From this equation we can obtain flow velocity of flow. Velocity of flow is equal to 0.6 into root 2gh. So substituting the values, we will obtain the flow velocity Vf1 as Vf1 is equal to 15.7 meter per second. So the overall efficiency, equation for overall efficiency is equal to P divided by WQH. Since this is also a reaction turbine, the equations will be very much similar to the reaction turbine, that is Francis turbine, we had already discussed in our earlier videos. So P is given and we know H, W and rho. From this equation we can obtain value of Q. Q is the discharge from the turbine. Discharge from the turbine is Q. So Q is equal to, the equation will be P divided by WH into efficiency. So from this equation, substituting the values, P is equal to, we know that P value is 22,000 kilowatt and W is equal to 9.81 into 1000. So here also 1000 will come. This will cancels out. So we can take it as 9.81. So here it is given as 9.81 and H is given as 35 and efficiency, overall efficiency 0.88. So from this equation we will get the value as 72.8 meter cube per second. Next, we have the value, that is, and the discharge value is with us. So from this value, uh, so the discharge is known. So we know that discharge is equal to area into velocity. So area is equal to this, we had already discussed in our earlier video. D O square minus area is dO square minus dB square into velocity is velocity of flow Vf1. So substituting the values, we know that the dB value, dB is equal to 0.35 dO. So instead of dB, we need to substitute this value. So it is substituted here. So dO square minus 0.35 dO whole square into 15.7 is the Vf1 value, velocity of flow value. So taking dO square outside and substituting all other values, we will get it as 10.82 dO square, and the discharge we had already obtained from this equation, and it is obtained as 72.8 meter cube per second. So 72.8 is equal to pi by 4 and dO square into 1 minus 0.35 square into 15.7. So it is equal to 10.82 dO square. Therefore, dO is equal to root of 72.8 divided by 10.82 is equal to the diameter or outside diameter of the runner is obtained as 2.6 meter. So once we get this value diameter, we know that the peripheral velocity is equal to pi dn by 60. So here we can take it as dO, pi dO n by 60. From this equation we can obtain the n. So next parameter we need to calculate is the speed of the turbine n. Speed means the rpm of the turbine. So n value equals, n is equal to 60 u divided by pi d0. So 60 u divided by pi d0 is equal to 60 into 52.4 divided by pi into 2.6 is equal to 384.9 rpm. Next, specific speed of the turbine. So specific speed of the turbine is given as, so for the turbine the specific speed is given as n root p divided by h raised to 5 by 4. This is a very important equation, and you have to study the derivation for this equation, that I will discuss on in my later videos. Okay, for the calculation of specific speed, you need to by heart this equation. So this equation is exclusively for the turbine, n root p divided by h raised to 5 by 4. So p value is unknown, n value is known, h value is known. From this equation, so n root p divided by h raised to 5 by 4 is equal to, n is 384.9 into root of p. Root of p is given as 22,000 kilowatt. So here we take it as 22,000 divided by 35 all raised to 5 by 4. The specific speed obtained is 670.6. Diameter and speed of the runner of a Kaplan turbine developing 6000 kilowatt under an effective head of 5 meter. Overall efficiency of the turbine is 90%. The diameter of the boss is 0.4 times the external diameter of the runner. The turbine speed ratio is 2 and flow ratio is 0.6. What is the specific speed of the turbine? So this is the problem. So the given values are power, it is given as 6000 kilowatt, and head is given as 5 meter, overall efficiency 90%, and diameter of the boss is equal to 0.4 times diameter of the runner, speed ratio is given as 2, flow ratio as 0.6. So we know that u1 is equal to speed ratio into 2gh, and vf1 is equal to flow ratio into root 2gh. So from these two equation we can obtain the value of u1 and vf1. So u1 is obtained as 19.81, and the flow velocity is obtained as 5.94 meter per second. So the Ku value is known, H value is known, H value is known, and Kf value is known. So from this equation we can obtain these two values. Next we need to find the discharge. Discharge can be obtained from the overall efficiency equation, P by W Q H. From this equation we can obtain a discharge. So discharge is obtained as P divided by the overall efficiency into W into H. So 6000 into 1000 divided by the overall efficiency is 0.9. W is 9.81 into 1000, so 9810 into 5, and it is obtained that the value of Q is equal to 135.9 meter cube per second. So 135.9 meter cube per second is the discharge. So from the discharge we can find the diameter, outside diameter DO. So the dB value is given as dB is equal to 0.4 DO. Substituting this value here, so DO square minus 0.4 DO square, and taking DO square outside, pi by 4 into DO square into 1 minus 0.16 into 5.94. So from this equation, DO is equal to root of 135.9 is the discharge into 4, pi by 4 is taken here. So 135.9 into 4 divided by pi into 1 minus 0.16 into 5.94 whole raised to 1 by 2. 1 by 2 means the root of this value. Okay, from this equation we can obtain 5.89 meter as the diameter of the runner. Once we obtain the diameter of the runner, we can substitute the values in the equation, pi do into n by 60. From this equation we can obtain value of n as 60 u1 divided by pi d0. So once you get the value of n, we can substitute it in the equation for the specific speed. So n is obtained as 64.23 rpm, and the specific speed we obtained as 665.4. So substituting the values, n is known, p is known, and h is known. So from these values we will obtain the value for specific speed. So the value for specific speed is 665.4.